Hello, thanks for joining. This is part 2 of the video about the A-18 voltage distribution panel. In part 1 of this series, I had the panel drawn on the board and we pulled the panel circuit apart and redrew it as a schematic diagram, and then went ahead and calculated the total resistance, and then we found the voltages at each particular point on the board. They were of course the unloaded voltages, but then part 2, which is this video, we have to look at the loaded voltages again at each one of these points by putting load resistances onto them. I've done this video using Camtasia and using my in-class notes. You'll find that it's a little bit more complex than part 1, and there's a particular technique that we have to follow. It's very structured, and if we don't do the structure correctly, we will not get the correct answers. So please pay attention to each part of the video, especially the current dividers. I hope you find this interesting. This is Greg Moore for New South Wales TAFE. Hello, and here we are of course with the Camtasia recording element for the FA18 voltage distribution board. Part 2, the loaded calculations. Looking at the screen here, you can see I'm using an application on the Mac called Notability. I use this application for so many things that I do, both in class and in the studio. And just to give you an idea here, I've done recently some digital notes. You can see there. And I've done some other digital handout notes there, and AC notes. I know I visited AC this week. But anyway, let's move on. DC teaching notes. And what we might do is get rid of that side tab and just expand this out a little bit more so that we've got some more space to play with, so to say, on the screen. Right, loaded voltage calculations for the FA18. In video number 1, we looked at the unloaded voltages, and even as they stand, you need a good knowledge of Ohm's law. And in fact, before we even got to Ohm's law, you would have had to pull apart that board, be able to trace the individual tracks on the board. Luckily, it was only a single layer board, not a 2-layer board. And then draw the schematic diagram, put the schematic diagram into a semblance which we can recognize as being a voltage divider, and I like to do that in a vertical column. And then we applied Ohm's law to that, and simply we got the current, we worked out the total resistance, we got the current, multiplied that current by the bottom resistor first to get 29.96 volts. Then we added that resistor 220 to the 560, multiplied that resistance by the 48 milliamps, and we got 37.56, etc. But they are only the unloaded voltages, and all voltage dividers supply some piece of equipment, and in so doing, the voltages change because you've got different currents flowing out through each segment on the board, and therefore we have a current splitting situation. So we have to use a thing called a current divider in part 2. In fact, we'll be using the Kirchhoff's voltage law, Kirchhoff's current law, and a current divider, looking at a ratio to find out the 2 branch currents that leave a particular node. So let's just have another look at the board. That was the board from last week, and there's the edge connector or the socket. There's the edge connector numbered up to pin number 22. Various resistors on there with luckily all of the values written, but the colors of course match the resistance, such as 220 was red, brown. We had outputs V sound, V decade, V bias. We had 91 volts DC coming in and feeding the board, and we had a link across this section on the socket arrangement here. All right, so let's go back up and have a look now. In the notes, we were told what the loaded resistance values were. Off the bias, it was 12 k ohms going to ground. Off the decade, it was 6.8 k going to ground. And off V sound, it was 5 k ohms going to ground. And I've drawn these load values again next to the voltage divider, and I've said, here's the big story. The loaded values are required. So what the heck do we have to do? I've got question mark volts, question mark volts, question mark volts, and this becomes quite a difficult problem for beginners learning about electronics. Unloaded itself is hard, loaded is much, much harder. Step number one, always redraw the circuit. You could probably work on the circuit as I've got it pictured here, but I like to redraw it, put the resistors so that I can draw some nice loops around them and work out what's in parallel and in fact what's in series, and then we're going to have series parallel combinations here, and we're going to have nodes where current enters and current forks and leaves. So step number one, redraw the circuit, and that is in fact what I've done. Absolutely go ahead, recheck the values, because now we have to do some maths on this circuit to find the total new value of resistance. Always start at the end furthest away from where the voltage enters the board. So 6.8k, 560 ohms, they are the resistors which are the furthest away. So first of all, they are in parallel. So I could either use product over sum, or I could use the sum of the conductances to the reciprocal of the conductances to find out the new resistance there. Whichever way you decide to go about it, it was the answer was 517 ohms when you put 6.8k in parallel with 560 ohms. And then you can see here 517.4 added to 220. That's this 220 resistor here, which is in series with this parallel network which we just discussed, to give us 737.4. But we're not out of the woods yet, because you can see I've got a blue loop around here, and that blue loop, I've got the 737.4, which we just had, in parallel with 5220 ohms, to give me 646.125. And that is the equivalent resistance of everything inside that particular blue loop. But then, of course, that 646.125, it's in series with 560 ohms. So we have to add that to get 1206.125. Still did it in blue, just my preference, because I've got another green loop here which encompasses everything we've discussed, but now including a 12k resistor. So 1206.125, here it is here in green, in parallel with 12k ohms. And that 12k in parallel with that works out to be 1095.97 ohms. Then, of course, that is finally in series with 550 ohms, the sum of 330 plus 220. You can see I've added it here. I've done it in grey colour to get 1645.97. That is my total resistance coming into our circuit. So the total network resistance there is 91 volts, the applied voltage, V equals I equals V on R, and then 91 volts divided by 1645.97 to give me 55.29 milliamps. Now, at this point, you could keep going, sure, but if you've got access to a circuit simulation package, it's probably a smart point in time to go ahead now and just put the values into the simulator and find out if you've got the matching current. So let's go ahead and do that. I've got the simulator here. We're looking for 55.29 milliamps. Here's my circuit simulator. This is done with iCircuit on the Mac. And 91 volts, there's all my resistors in the original network. Here's my loaded resistance values on the right. And if I just click on anything up here, I'll get the, in this case, I'd get the voltage across that, which is 12.16 volts over here. but the current going through it, 55.287 milliamps. And even if you just go onto the wire there, you can also see 91 volts, total power in the circuit 5 watts, but 55.287 milliamps, we're on a winner. We've got the right value. That means we've got the right resistance. So that's fantastic. I'm happy with that. All right, moving right ahead. Moving right ahead. All right, what do we got to do now? Step number 2. Well, step number 2 would have been to get the current. Step number 3, calculate the voltage drops. So we had the first 2 resistors, 550 ohms. We can calculate the voltage drop across that by what I've done here in red. 91 minus the current times the 550 ohms to get 60.59 volts. And that's the voltage at this first node in the circuit with 2 orange takeoff points. So some current coming down through the 12K, some current going along to the right through the rest of the network. Step 3A. And that actual 60.59 volts, that's actually the 12K is V bias. Let's just go up and have a look at that. There was my 12K. That's the V bias takeoff point. And now we've actually solved the first part of the riddle. 60.59 volts on V bias. Step 3A, we need to use the current divider rule. The current divider rule is just based on Kirchhoff's current law that says the sum of the branch currents leaving a node is equal to the current entering the node. And if it doesn't, well, you've got some leakage current there somewhere. So if everything goes well, we can use this current divider rule. The current into the node times the equivalent resistance divided by the resistor we want to find is going to be equal to the current going through that resistor that we want to find. You'll find this equation in Floyd and a few other books. And historically, I know when I went through and did my first training, we were taught a slight variation of this rule, and it could only be used for 2 resistors, whereas the rule that I've got here can be used for any number of resistors in the network. So this is the only current divider rule that I teach nowadays. Just get the total equivalent resistance for the network, divide that by the individual resistor, multiply that by the node current coming into the network, and that'll give you the current for that particular resistor. So case 1, case 2, because there's 2 forks in this, 5.05 milliamps going through the 12K resistor, and 50.24 milliamps flowing into the rest of the circuit. And that's the one that I'm interested in. Tiny little bit of fixing on the fly here. I can see that I've got a small problem in my circuit. Oh no. So we just plug in the graphics tablet, and I hope this all works under camera control. It should do. 50.24 milliamps. Silly boy, 50.24 milliamps. $50.24 milliamps, that's better. And the 5 milliamps is going down through that other critter there. 5.05. Milliamps there. Okay, all right, that's looking better. All right, so after we had that tiny stuff up there, and we've now gone ahead and we've rectified that. We've got 50.24 milliamps flowing through the 560 ohm, and of course that is 1206.125 ohms if I was to put a circle right around all of those. That 5.05 milliamps is only going down through the 12K because, of course, the larger value of resistance is going to have a smaller current compared to the smaller resistance from the rest of the circuit. So we had. So this next point here, this next node, that's going to be the V sound takeoff point, and that's the V bias takeoff point. So we need V bias minus the current going through the 560 ohms times the value, 560 ohms. And because that's a subtractive process, we're subtracting that voltage from that node to come up with 32.46 volts at this point here. Brilliant. So we had to use, let's just retrack, we had to use a current divider because we needed to find out that we had 5 milliamps going one way, we had 50.24 milliamps going the other way, and then we can use that 50.24 milliamps voltage drop across the 560 ohm resistor to give me the next node voltage. And that next node voltage becomes quite critical because we need to go ahead and do yet another current divider on that to continue getting the rest of the voltages and currents in the circuit. So I'm going to go back to iCircuit and I'm going to check this again and just make sure that I've got the right voltage. Math says 32.46 volts. Let's go and have a look. 32.46 volts. Ah, very interesting. Now we've got a 220 ohm resistor here. 32.46 is on this side, the main network side of the 220 ohm resistor. So that's not going to be the V sound output. V bias was fine. It didn't have a series resistor with it, but this one does. 32.46, check, that's great. But this side, 31.09. Oh, we've got to do a bit more maths. So that's something to keep in mind. That would be a trap for young players, definitely. All right, so hence I've got here, but there's a 220 ohm in series. I220 equals 32.46 volts divided by the 5220. That's going to be the 5,000 ohm resistor plus the 220 in series to get 6.2 milliamps. Multiply that by the 5,000 ohm resistor and it tells me straight away 31.09 volts across it. And yay team, that's exactly what we got. So we're on the ball, we're on the track. All right, current divider number 2. 32.46 because it's going to be before that 220 ohm that we just talked about. So I've got that net 5220 there. 32.46. I've got to use the current which is flowing into that node, 50.24 milliamps. And then I've got to multiply it by the REQ at that point there, which was 646.125. Divided by 5220, 6.219 milliamps going down through him and 44 milliamps going the other way. And then again, what I can do, I can multiply that 44 milliamps by the 220 ohm resistor. I've done it down here. Subtract that from the V sound point. That'll give me the voltage at the V decade point. Finally, 22.78. Let's go and have a look at the iCircuit. 22.78 volts. Thumbs up, we've done it right. All right, a lot of work involved in doing this type of job, as you can see. You have to redraw the circuit. You have to use 3 rules: Kirchhoff's voltage law, Kirchhoff's current law. You have to use current divider. When you redraw the circuit, you've got to start from the furthest end, and then you've got to work your way back. You've got to work out R total first, and then you've got to work, that'll give you then the ability to work out the circuit current total, and then come from the battery voltage side of the circuit and work your way back across, solving all of the branch currents and all of the voltage drops to get those final values. All right, this has been Greg Moore for TAFE New South Wales, and that was quite a large explanation, but it's online, and I hope that was really helpful. Happy to do it for you. Okay, see you next time.